It is very hard to talk about electron orbitals and really explain them in a way that makes sense in real life. This is kind of a picture that I have in my head that helps me. If you look at an amusement park ride, like if this is one of those swing rides, you know, where it's like got the people out here, you'll know in your head, you know that these swings are there. But this picture is showing you that they are somewhere in this region and they're all moving so fast that they're blurring it and they're in that region. You can also tell when you're looking at this picture, though, that like the electrons or the swings are not out here. We know that they have to be in this inside section. We know they're spinning and moving really, really fast. And we can tell that they're kind of in like this region. That's kind of like an electron. It's not in all places at the same time. We're not trying to say they're in all places. But if you take maybe like a snapshot over a long period of time, or you can think of it as like overexposed camera film, then what you end up with is a shape that represents what the electron's doing. Now, to make it even more complicated, the electrons have all these wave properties, and they can also be representative waves. And so you can think of this area also as kind of like a circular guitar string that's like twanging on a certain frequency. It's kind of like that too, but it's more and less than that. These are just very hard to conceptualize. But that's the beginning of a picture you want to look at. And I do have some other simulations. So the calculations for the region that the electrons could be in, we're only going to make us understand out 4 levels, is one is very nice and simple. It's the sphere, and that's where the hydrogen electron was, and that's one reason why he could do these calculations. The next area that it could be in was the p orbitals, and there's this word called degenerate. Degenerate means equal. So a p orbital, you can tell they have the same kind of space. This one is just sideways. This one's up and down, and then this one is like behind your screen and in front of your screen. They're the exact same shape. There's no preference to be in any one of the shapes. They just can pick one, and off they go to the races in their movement. But that they'll stay in this vertical kind of shape, unless they're excited or something, or they'll stay in this kind of a shape. The next one has a lot more oddity to it, and that's these d electrons right here. And so these d shapes, the first, let's see, let me find the ones that are similar. This one, so that shape is like this one, and they're just like in different directions, kind of. And then also this one is in different directions. It's kind of like if you take this is like on that axis, and you put it like up and down, you'll end up on this axis. So these 3 are the same shapes, just moved in different directions. And this is the one that's kind of like in the in-between space of all of those. So those are really the same shapes. They're just kind of angled in all different ways. And then this one obviously is not at all looking the same. But all of these are all, if you do math and calculations with it, they are all the same. They come up to the same sums of the region that the electrons are going to be in. And then the last one, we will not be dealing with the Fs as much, but you can see how many options you start getting when you have these different electrons. So there's 1 s orbital. You can see there's 1, 2, 3 p orbitals. You can see there's 5 d orbitals. And if you count on 1, 2, 3, 4, 5, 6, 7, there are 7 f orbitals. Not only are there different orbitals, but they fall on different energy levels. And every energy level starts with an s. So our first energy level, I'm going to try to build this over here, we'll have an S, and that's our first energy level. You saw that first energy level, you know how it was, that's the nucleus, so it's like around the nucleus. It's the closest one around. Then our next energy level, it's bigger. You remember it like it was further from the nucleus. So when we put him on there, whoops, it's going to be bigger and on top of. So you can see how he's on top of him. It's going to cover it up when I let go. So that's like our second energy level. And then with our second energy level, we have this. I'm going to make it something that fits. So we'll have something there. And that's on top of that other area. But they all have their own spacing. So again, it's hard to make these kind of fit. So do you see how this one's fitting in? They're not really crunching into each other's territory, even though these pictures kind of look like they are. They aren't. Let me do another one. And again, these are all 2p orbitals. And then the 2 doesn't have any room for any other electrons. So then we go up another size, and we have an even huger s orbital, see? And it's bigger than all the rest of them. So he gets laid on. We end up with 2 electrons there. All these all have 2 electrons. So he's larger. And then we have larger p's. And again, that's layered on top of everything that's in there so far. So we have larger p's, and of course we have to have all 3 of them. And it's in the 3rd energy level that there's enough electrons in there that you can also put, so see how they're all in there? You can also start layering in the d's also. You can see how complicated, maybe you could imagine how complicated math is going to be to put all of the rest of these d orbitals in there. This simulation does a really interesting job. I really like it. This helps you see something as, maybe like imagine them as being dots. So as soon as it pulls it up, we'll go ahead and we'll look at this simulation right here.